I'm Jenny Lynch and I'm the CAASTRO School Education Officer. So I've been with CAASTRO since June last year, and my background is in physics and science communication. I worked for many years for Questacon, doing outreach programs for schools, and I also worked as a freelance science communicator, developing classroom activities for children and science shows and that sort of thing. So just to give you a bit of background about me. But first of all, what is CAASTRO? Have any of you heard of CAASTRO before? So yeah, a couple of you have. CAASTRO is the ARC Centre of Excellence for All-sky Astrophysics, which is a bit of a mouthful, so we call it CAASTRO. And it started in 2011 with 7 years of funding from the Australian government. It's made up of scientists at 7 universities and other organisations across Australia. So we have 7 partner universities, and it's based on Australian and international collaboration. There's currently about 180 members of CAASTRO. So what does CAASTRO do? Well, it aims to address fundamental unsolved questions about the universe. And to do this, the scientists are grouped roughly in 3 groups, or 3 research themes. Some of them work across more than one theme, but I'll just go through the types of research that CAASTRO does. The first group is called the evolving universe. So they ask the question, when were the first galaxies forming, and then how have they then evolved? And here are just a couple of the tools that they use in the research. On the left there you can see the Murchison Wide Field Array. That's in a very remote part of Western Australia. And that's used to look for the epoch of reionisation, which is that was the time in the evolution of the universe when the first stars began to shine. The other antenna there, it's a conical antenna called bighorns, that's also in Western Australia. So these are both radio telescopes, and compared to optical telescopes, radio telescopes like these allow astronomers to look at much more distant objects in the universe. You might recognise this telescope. This is the Parkes Radio Telescope in New South Wales. This is one of the tools used by the Dynamic Universe team. So they look at the high energy physics that drives the rapid change in the universe. And one of the phenomena they look at is something called a fast radio burst. So this is a really intense radio signal that comes from space, and nobody really knows what fast radio bursts are coming from. So they're trying to collect more and more data about them to try and work out what's causing these signals. And finally, and possibly most bizarrely, we have the dark universe team. So they look at the dark energy and dark matter that are in the cosmos. One of the projects they work on is the Australian Dark Energy Survey, and this aims to collect data on about 3,000 Type 1a supernovae. So a supernova is a very bright object in the sky, and they've been really important in a lot of studies into dark energy and dark matter. So that's just a really quick overview of CAASTRO research. And here are about 100 of the CAASTRO researchers in the Blue Mountains last year at one of their research meetings. So I'm going to hand over to Scott now, and he's going to talk to you about some of the work that he does.
Okay, so just to give you a little bit of background about who I am, I've worked at the University of Sydney probably for about a decade now. I both lecture here and do research. Before that, I worked at the Anglo-Australian Observatory, or as it's now called, the Australian Astronomical Observatory, for about 7 or 8 years, and before that I was in the UK for a few years, and that's where I had my undergraduate and postgrad education. My focus really is on understanding how galaxies evolve over time and trying to pick apart galaxies. So I'm going to try to give you a little bit of a flavour of some of the research we do here in CAASTRO. These are just a few of the images of the sort of bits of equipment that we use, as well as the data. But just to start off with, I just make the point, and I'm sure you're all really aware of this, is that galaxies are immensely complex, right? This is a single galaxy that probably looks something like our own. It is, has 100 billion stars. It has gas, dust. It probably has a black hole in its center that's maybe 1 million to 1 billion times more massive than the sun. And it has dark matter that actually dominates the mass of the galaxy. It's horrendously complicated. All these different elements interact with each other. And so not only have you got to try to pick apart each element individually, you've got to actually try to understand the interactions. Right? And that's a large part of the complexity is understanding the interactions between different parts of a galaxy and how they evolve with time. There are various features you can see here. I mean, just looking at the colour, in the centre the galaxy is relatively red. That tells you it's dominated by relatively low mass, cooler stars, because the high mass, hotter stars have died. The high mass, hotter stars are blue, so you see those in the outskirts, so the star formation has happened more recently in the outskirts. And so one of many things we try to figure out is where new stars are forming in galaxies. That's just one galaxy. The universe is awash with galaxies. Here's just a montage of different galaxies that have a rich variety of structure. Most of them are rotating, and that's essentially a conservation of angular momentum reason. As gas clouds, things collapse, angular momentum is going to be conserved, you're naturally going to get things spinning, right? So, but not every galaxy does that even. So the question is how on earth we pick apart this complexity and try to understand how galaxies got to the point they are today, how they look, why they look the way they do now. Probably the most powerful way of doing that is spectroscopy. Okay, so we sort of mentioned a little bit about that earlier, but you can take the light from this galaxy. Here's just one example. You put a little aperture down, a little red circle, and you collect the light from that galaxy. Typically what we do is we take an optical fibre, point it through the telescope, the light comes down the optical fibre to a spectrograph, we get a spectrum. And this is just the wavelength, red to blue, and the number of photons, the amount of light we're collecting on this axis. You see this rich structure in this spectrum that tells you a whole range of different things. Right? It tells you, for example, in this case, there's a very weak little blip here which happens to be hydrogen gas glowing in this galaxy, which tells you that a certain amount of high energy photons are ionizing hydrogen atoms and causing this glowing gas, but only a very small amount in this galaxy. You see this overall blue, sort of reddening of the spectrum. There's much less light at the blue end than the red end, which again is telling you that you've got old stars in this galaxy. And in fact, you can look at all these different features are absorption, say for example, in magnesium, in calcium, in sodium, calcium again, sulfur, a whole range of different elements that allow you to build up the chemical history of the formation of the galaxy. But that is just one little point in the middle of the galaxy, and it's kind of like figuring out how Sydney works by just looking at the CBD. So you actually want to go one step beyond that, or maybe several steps beyond that. And so what we're aiming to do is to build up three-dimensional pictures of each galaxy. So the way we do that is by taking data that has both a spatial dimension, so you've got a spatial image just like the images before, but at each point on that spatial image we also have spectroscopic data. So we have a spectrum at every point. So you essentially end up with a data cube. Okay, so you have 2 dimensions on the sky, spatial, and then 1 dimension which is the wavelength of the light. And suddenly, instead of having an average measurement over the entire galaxy, you have this resolved information that tells you what's going on relatively across the galaxy.
So how do you find out what's beyond that point? As in, how do you do the depth element of it?
So the depth is wavelength, right? So it's not quite 3 dimensions in the classical just X, Y, Z, but this is wavelength. And so, for example, in our previous spectrum, right, this is sort of blue to red, you can imagine having a spectrum like this that is on every point on this galaxy. Right, and so what you can then go and do is take your instrument, and instead of putting a single fibre in the middle of a galaxy, you have a mosaic of optical fibres that cover the entire galaxy. This is just a next generation one that we'll put on the telescope in a year or two. When you do that, you suddenly open up a whole new array of information that you have. So here's our same galaxy we showed before. Here's where this fibre landed. The colour scale here is just the amount of hydrogen gas emission. The red is where you have a lot of hydrogen gas emission, the blue where you have very little. So in the middle, there's very little there. Right? This is what we saw here in this little blip before. But in the outskirts, suddenly you have this huge amount of emission that's coming from gas that's been heated and ionized by newly forming stars that you were completely oblivious to because you only looking at the centre of the galaxy. The second of many, many other things you can do is you not only can you measure the amount of light coming from that from the hydrogen gas, you can actually measure the wavelength of that hydrogen gas. And now this is the hydrogen Balmer line. It's sort of first transition in the Balmer sequence. And we know exactly what its wavelength should be. But this galaxy is rotating. And so when you measure the position in wavelength, you find that this side of the galaxy is coming towards you. So this is just a scale in velocity. This is coming towards you. This is going away from you. The galaxy is rotating.
Like Doppler.
Yeah, so it's a Doppler effect is what we're using here. Right, so just using the shift of the wavelength to measure a Doppler effect. Now this is immensely powerful because not only are you seeing the visible contents of the galaxy, you're measuring motion. The motion is due to gravity. So you're measuring the total mass there, including dark matter. So it's an immensely powerful technique. That's just a flavour of just a little bit of the richness of the data that you can get from this approach. The real power, though, comes in the fact that you have such a diversity of galaxies that you need to observe many thousands. The only way to do that is to build instruments that allow you to observe many galaxies at once. So here in Sydney, for a long time, we've been developing in the astrophotonics lab with the various people, Joss Van Hawthorne, Julia Bryant, and John Lawrence, who's at the observatory. This new instrument called SAMI, we take optical fibres and we etch away the outer cladding using hydrofluoric acid, which is nasty stuff. We get somebody else to do that. And then fuse them together. So you get a very close packed filled array. And then we have a dozen of those. And each one of those you position on the position of a galaxy. And you plug into one of these plates here. This is on the top end of the telescope. And then you stick it up here. Right, so this is the Anglo-Australian telescope. In Coonabarabran, for scale, there's a chair, so somebody's, person's that size. And then suddenly you've got this large aperture telescope that is able to collect data to measure the spins and the motions and the star formation in cross galaxies with many galaxies at once. This is just make the point that it's actually in the top end. This is that black thing that you saw at the top. Right, is actually this ring here. This is one of our PhD students, Sam Richards, who was, when we first commissioned the instrument, was sat in there all night long, sort of whizzing around the sky. Interesting place to see it. It was cold as well. It was the middle of winter, but he survived it. He's all right.
How big is that bunch of optical fibre ends like in that image there?
So here, this is a millimetre across.
Oh, it's millimetre.
That's a millimetre, yeah. So each fibre bundle, each fibre is 105 microns. Right. And so, I mean, one of the art to this and the complication of this is that you want to minimise the gaps in these things. And so an awful lot of work in the astrophotonics group here, led by Joss and Julia, went into sort of developing that technology. So there's a very strong crossover between the sort of the applied sort of technologies of photonics and instrumentation that goes into astronomy. And so this is an example of the data we get from SAMI. Okay, so here's the image of a galaxy, as we saw before. You can just put on a scale sort of the amount of just straight light, the total amount of light you see, and this is what you get. You see obviously brighter in the middle. But then we can measure the motions of the stars. In this case, the galaxy is rotating. We can measure where that hydrogen gas is glowing. And you can see it's not uniform, and it's not where the old stars are. It's actually in the outer parts. And we can separately measure the gas rotation, which is actually a little bit different. And all this comes from this being able to analyse the spectra. So again, it's the same picture again, wavelength along the bottom, red to blue, and just the amount of light, the flux. And these are just two examples. The blue spectrum here is where that we get from the middle, and the red is where we get sort of somewhere on the outskirts. And all these little features in here contain that information, that encode that information about the velocity of the gas and the star separately, about the amount of gas that's ionized, about the age of the stars, about the amount of heavy element content in the stars, and lots more besides. So our current plans are to build on this, and in fact we're generating a survey at the moment that's already observed over 2,000 galaxies with this instrument. And so we're going from these images, they're just multicolour images, to maps that show gas emission for every galaxy, and then go to show the velocity distribution, and then therefore get the dynamics, measure mass in all these galaxies. So this is an ongoing project. We are probably a little over halfway through, so we've got another couple of years to run, but we will we'll have about 3,500 to 4,000 galaxies by the time we finish the survey, which will help us to pick apart how galaxies vary depending on where they are in space, what their masses are, and over cosmic time. And I think I'll stop there. Thanks.